how I can write OpenTPS code to simulate a proton, a number of proton particles going through uh, a, a water phantom of certain size, a water cube of certain size. And yeah, I'll just make a new file and I'll type along so that you understand it properly. So first I have to import system module, and then from pathlib import path. This is to, I'm doing this to make the simulation as similar to a Fred example, which I will tell you in later on. And of course, the most important module. And this part here I'll use later on to get the beam parameters, which I can easily manipulate, not touching the original file. Okay, these are some syntax. Then I import I have installed OpenTPS on a server with 28 cores. OpenTPS is a method to calculate dose using the Monte Carlo engine known as MCsquare. Many core, something MCsquare, I forgot the full form. Many core, I have to look it up. Yeah, so MCsquare is the dose engine, or the algorithm which calculate the dose and verifies it. So RT plan, this is going to take some time. I'm worried because I'm not getting there's some kind of error. It's saying numpy, it's fine. Usually I should get the prompt of import, yeah, and when I type RT plan, no, something's wrong, something's not right. I'm connected to the server. I'm gonna delete this again and try again. Open TPS, something's wrong. Why is that the case? Perhaps I'm creating the, wait. Yeah. So because the file has to be in the same folder where the OpenTPS processing and the MCsquare source code is present in the same folder. So now it's coming on its own. Now all I have to do is like enter, and it will be fast. I hope so. Party plan, yeah. Import party plan, yeah. That will how I will put the cube, the water phantom. OpenTPS core, OpenTPS core. That's import read scanner from. There are a lot of modules that I have to import, and all of them, this core, all of this, when you install OpenTPS, you will see these folders and the source code, and you can change the source code as you want. Now the processing files. Yes, everything's going fine for now. From OpenTPS core, OpenTPS core processing those. So with this new version of OpenTPS, you have to define what particle. You cannot define a general ions. You cannot use the ion plants, but you have to go for specific. For example, I'll do here the dose calculated by protons. So this is the new change which has to be implemented, otherwise it won't run, and it took me a lot of time to go through that. And maybe later on I'll show you all these files and how it organizes and how it is placed in the folder. Core. Okay, dot OpenTPS dot core. Now data plan. You see, for photon it's different, for proton it's different. Earlier it was named under ions, now it's different. When you install OpenTPS, try to copy the branch, the dev branch, not the master branch. I guess now it's called the OpenTPS version 2. Let's core OpenTPS as usual, core data. I'm pretty much sure I'm going to get some serious errors, but we'll figure it out together. Plan, of course, proton. This time it's proton layer, and then I'll import plan proton layer. It's much easier with an software like VS Code to write code. Earlier I was using simple Python in the terminal, which was very time consuming and took a lot of effort, and still I did not get the result. But yeah, now it's easier. Import CT image. So CT calibration. Hold on, why is it not coming? Because it's a variable that I will define. Read scanner to this is to read the beam file. The beam, it's named as BDL, beam dose layer. I don't know, I'm not sure, but it has all the information about the beam, which you can change to make the simulation as per requirement. So I did this simulation in order to, oh well, the name is wrong. Well, in order to compare Monte Carlo algorithm which runs on GPU and this MC square which runs on CPU. And to do that, I made the parameters same, which was putting the nozzle, the beam nozzle, around 40 centimeters away from the water phantom, which I did it, which I did it in the BDL file and saved it as another copy. I don't want to um, make changes in the original one, so that it will be ruined, or maybe later on it will be difficult uh, uh, to find, or yeah, to just make things smooth. So that's the file I changed. I will show you actually what I changed. Where is it? Let me find it for a while. It perhaps Lawrence. I'm running this. I will run this um, Monte Carlo code, this OpenTPS or MCsquare code on Lawrence server, which has 28 cores. I think I said that. OpenTPS core, and yeah, I will show you. So if I go back, yeah, this is my thesis work, of course. So this is my Lawrence folder, the server. If you install, I will make another tutorial about how to install Lawrence perhaps in future. So you go in the OpenTPS. I saved my file as import sys. I should not. I should rename it. Rename. Well, I'll do it later on. I'll show you. So you go here. If you follow this, you can follow this path by the module names we wrote here. So for example, for BDL, we will follow this one. So now we'll go in processing, dose calculation. Yeah, here you see dose calculation protons, and then after protons we go to wait, MCsquare, and here you have the BDL file. So I changed the parameter. What I changed is I wanted to make the nozzle 40 centimeters, which is 400 millimeters away from the water phantom. I changed that. This is about the magnets which steer the protons, so I did not change it at all. I kept it as it is. Now this range shifter weightage, it's about uh, what is there in between the nozzle and the phantom. And then I wanted to keep the energy with the beam divergence with full with half maxima of 5 MeV, and I changed that by changing this parameter. So you know by using the formula EWFHM is equal to 2.35 times sigma. Anyway, these are the changes I made so that I can make the simulation as I want. Anyway, I'll move further on, and now this BDL file which I edited will use those parameters to, yeah, now I do the planning. I do the plan, I append the beam. My beam is proton beam. Why don't they give the brackets? And then plan beams, gantry angle. So this gantry angle, if I think if I'm right, it's going, when it's 0 is going from, like, the beam is going from minus z, like you kept the nozzle at z equal to minus 40, and that the protons come out of it from at minus 40 centimeter at z equal to minus 40 centimeter, and it goes towards positive z direction. That's what it means, the gantry angle. If you do it 180-degree, it will be opposite. It's plant proton layer, and this 150. So what energy am I sending? What energy of proton am I sending? Is it 100 MeV, 100 MeV, or 150 MeV right now? Because I just did that a few hours ago. I'm trying to do a simulation for 150 MeV. We can do it for another energy, but let's go on with this one. Yeah. Now I say where the beam should fall. So it says I'm planning to make the cube as 200 centimeter cube. This is x and this is y. So somewhere in the middle of my beam will fall somewhere in the middle of x and y plane. And this is about, this says about monitor units. I kept it as 1. No. Yeah. So as I said, I'll keep my cube as 200 millimeters, not centimeters. Yeah, 20 that is 20 centimeter cube. And then I create this object, city image. Let's call this city image, or this phantom, as city. Now I'll use in CT we only have Hounsfield units. I have to convert that into relative stopping power. How do we do that? Oh wait, why is it not happening? There is a inbuilt code for doing that, but why is it not loading CT calibration? It should not be the case. So CT calibration dot, maybe I have to type it out. So I have my Hounsfield unit will be converted into relative stopping power of water, of course, here, and these are built in, and I convert this yeah, so I am now making my phantom the cube of 20 centimeter cube. Okay, and there I have, no, this one, yeah, this one. There I have my phantom. Now I bring the Monte Carlo code that calculates those. One of the annoying feature of VS Code is if you are giving the name, you can also give the bracket with it. And Well, I have 28 cores, so it's quite fast, but still I'll do it for MC2. I'll do it for 1 million particle. And first let me make sure it works. 7. So yeah, before in OpenTPS version 1, there was no we don't have to set the monitor units. It has something to do with monitor units if I'm not wrong, but now we have to set this meter, otherwise the program throws an error. Now can I change this name? It's not proper. Reopen with, how do you change? Anyway, I'll run this and see what error it throws. So first I have to activate the the environment, which is I have noted in Notion, and here it is. I can't remember all of this stuff. Hopefully with practice it comes. Yeah, now my environment is the OpenTPS environment is activated. cd OpenTPS. I hope my file is here somewhere. Yeah, this weird one. Uh-oh. Python import. It let's hope it runs. Voila, it runs. So it's not as fast as GPU powered Fred, but still it's fast. The whole idea of this tutorial was to show you how to write a simple code in OpenTPS and run it. So it took 21 seconds for, okay, I had 10 million particles, but for 1 million particle it hardly takes maybe 5 seconds or something. What else I can, so yeah, it would be nice if I show you the results. So for that I have made a Jupyter file for just plotting, because it's very difficult to plot all the axes through. No, Jupyter. Hope it runs. Yeah, perfect. Where is it? Not Lawrence. Docs. So yeah, whenever I run the MCsquare code, the output, wait, Lawrence, yeah. The output is saved automatically to, I'm still working around, I'll find a better way, efficient way to save the output. And this is the output, the DOS MHD file and DOS raw file. You also get the pencil beam, this text file which says where is your ISO center. I mean, it says it's I think this is Z direction. I'm not sure though. This is Y and this is X, because I'll show you how. If I change those, but I'll not confuse you. So this is how you get the output, like where is your beam, how is it kept and stuff. So you can check that. Now I'll show you. This is to load my dose MHD file as an array using simple ITK module, which is quite handy. And if I press enter, why? Because okay, I need to import matplot pyplot as plt. Oh no, matplotlib. Grammarly helps me. So you get the depth dose curve. This curve actually matches with my Fred, which runs on GPU. So I get in MCsquare, I get the Bragg peak at around 154 centimeters. In Fred, I get it around 153 centimeters, which is quite good. Even the dose right here, it's in electron volts per gram, and Fred gives in gray, but when I convert, it's almost similar. Anyway, the whole idea was to show you how it works. I hope it helps.